Well, we are going to start our panel section. Thank Andrew. Oh, hello. Of course. We just talk about that all the time. Yeah? Well, welcome everybody, those here, those in the internet, to our panel section. The panel section would occur the following way. We call all the speakers during the day of yesterday and now Professor João Justo, and they have 10 minutes to make a statement, a position statement, and then we will open for discussion with everybody, and also those on the internet. I'm not sure if they can send questions. And after that, everybody will have 5 minutes to a final position. Okay? So we call in the order of presentation Professor Jim Reddy, please. Professor Shimonov. Professor Adrialin. Lucius Cyberman. And João Justo. So please take a seat. And we follow that order, starting with Professor Jim Reddy. Yeah, you have 10 minutes. Yeah. Ah, okay. That be 10 hours, not. Winter?
Okay, so is it working?
So.
Maybe there is a button. Okay, good. Good morning. I did mention few things yesterday in my talk. Now I have prepared a little bit more detail on. So there are two sources. One that came in 2008, I think, one that you referenced about NAE. And then there is a 2017, Royal Academy also has one. But they have very good points, but things are changing. So I created my own list here. So materials design is one of them. And as I mentioned yesterday, since my background is mechanics, I'm going to say most of the things from mechanics point of view. So what happened over the years is, I think the mechanics community themselves shot in their foot by claiming superiority and really staying away from the common folks by saying, okay, this is rational mechanics and very highly sophisticated, and all these people are not, they don't understand. It's like a priest who knows the Latin and expects everybody to just chant without understanding it, right? So mechanics, because of that, I think what happened is it is ignored now. It's not as much respected. I don't want to use the word respect, but they are not really considered key players. So, but I think the mechanics has a significant role to play. So what I'm saying is the responsibility is of the mechanics community to deliver what is needed without claiming this superiority. Okay? So having said that, now, so the mechanics community has a long way to go on this in the sense of materials design, working with the materials group, material science group, because they develop materials, but where are they going to be evaluated? They have to be evaluated in the context of application. And when application is involved, there is mechanics involved. So that's what my point is. Okay, the simulation of manufacturing processes, and this is again, there is a lot to be done in this area, whether it is composites or any kind of heterogeneous material systems. So there is a very, very deep understanding is required, but we have to go all the way to technology transfer. It's not like talking about second Piola-Kirchhoff stress tensor and green stress tensor and so on. This is not the thing that those are useful, but you have to go to the extra step to deliver in the community where people understand and they get into applications. And this is another, there are two things that I said yesterday. One is the harvesting, and second is to actually delivery. So the harvesting, I mean, all of you probably have bigger ideas about nuclear energy, this and that. But I'm talking about harvesting the energy that is being wasted around us. Okay? And taking steps to do it. Even though they may be small amounts of energy, but they can be used very efficiently for warming your clothing or warming or powering your cell phone and so on. And second is this delivery. So that is really, again, it may lead to other kinds of inventions, because you don't need to cool or heat every cubic meter of space in a place. You may only need to do it in a selective way. So this delivery is another important area. And then mechanics and computation, this is really, it can be anywhere. It's not, by the way, the numbers don't mean anything. I'm not saying it's priority or anything. So, but these two go together because they are the kind of, important elements of anything that we do in solving the engineering problem. So, but you have to understand the, computation. We were talking about during the break. So now the benefit or advent of having abacus and ANSYS-like programs has made the users blind toward mechanics. What is behind the scenes? How do they work? If you don't know the limitations, then you think that everything coming out of the computer is right. So we need to have that education and complete understanding of the computational mechanics, means methodology. So, and there are a lot of things that are happening in terms of actual doing it, parallelization, whether it's sequentially or parallel. So simplicity is, of course, and practicality should be the drivers in all of these. You cannot just claim again, oh, how sophisticated it is, but again, it has to be very simple and practically useful. And internalizing mechanics in everyday life, meaning again, so the thing is, this is the comment I made to begin with. Everybody kind of made in the past that, oh, mechanics is a very high level subject, but I think it is not, really. Everything that we do in our life, it is really one kind of mechanics or the other. So we have to bring this into education. So these interdisciplinary things don't come by going in the same way as we did in the past, meaning you go through mechanical engineering slot or civil engineering or material science and then ask them to think like a multidisciplinary way. It cannot happen unless they are introduced to those subjects early on. and make them think like that. Means the problems you select in illustrating concepts, they have to bring multiple disciplines to work at it. Otherwise, people don't have that habit of thinking. It's like you already programmed one way. Okay? So this is another thing I have in mind. Analysis and design of custom-made parts. And this is again question of durability, which has a lot of... by the way, when I use the word mechanics, don't misunderstand it is solid mechanics only. It can be heat transfer, fluid mechanics, host of other things. So we must understand the durability of the parts that are produced using, any of the new technologies, whether it's a 3D printing or other types of things. But most of these are now used for custom-made parts. Smarter systems with integrated functionality and safety. So these can be devices, especially biomedical type, or sensors and actuators, but they should have not only smartness, but reliability, and that means some kind of safety included as part of the systems. And then machine learning with mechanics at play. So this is most of the time people are trying to say that machine learning will take care of everything. All I need is the data. But I think you also have to have mechanics understanding of the data. If you don't do it, then it will really sometimes it may lead to. Of course, it depends on the field. Certain like the example of tsunamis and earthquakes. Still, mechanics plays a role, but data is very, very important. Okay, so without the data, you cannot, just depend solely on mathematical models. Okay, so those two things, and I thought a lot and created these, but I cannot read everything. I will leave this with you, by the way, if you want to look at it. So this is another area. So depending on what really you're interested. So I put like a questions. Can I mend the body of growing child, accommodate for better living at a geriatric stage? Okay, so these are really challenging questions. It's not like a disease or something. You can plan. How do you do it? Can I mend the human body to make the person fit for a particular sport? See, this is almost like these horse breeding, all that, right? I'm not trying to say you have to clone people, but how do you make? See, just like we are creating mechanical engineers, civil engineers, electrical engineers, similar thing, right? For sports, how do we do it? So, can I come up with a training module that are tuned with mechanics and muscle training? Okay? So, and then challenges in space. This is, I think, I could have made it even nature, challenges in nature, that so that it includes geological phenomena, like earthquakes, tsunamis, and other things. But it is really very, very challenging area, and I don't think we will be able to solve things in near future, but we have to work at it. So, and then these are the things. I'll stop here. Some things that I mentioned here is a detail on demand. So devise better ways to bridge scales, spatial and temporal. Okay, so this is, I think, a very challenging area because especially temporal scales, like you want to do certain things real time, right? And then physics-based machine learning. So most people in that community, machine learning community, think that all they need is data and mechanics is not important. Okay, so anyway, I'll stop here because I think I took my 10 minutes. So let me see, then who is next? Thank you.
Okay. Thank you, Professor Nath.
Good morning. Thank you for the new update of challenges, Professor Reddy. I just took 2 slides and I tried to elaborate on cyber augmented collaboration as a gist of what I presented yesterday. So this is one of 2. Automation resilience, the big picture means cyber augmentation. We talked about it before. We explained the word augmentation, meaning helping, adding, improving, leveraging, and making it better. So with cyber today, the big picture is that when we look for resilience, including the challenges that Professor Reddy mentioned, we need to use the technology that we call convergence, including divergence with the cyber capability. So the challenge is now in number 2, major opportunities for innovation through new and better cyber collaborative models of systems and products. So we talked about the service orientation where we combine services and products, and we can do that now with more powerful cybernetics models that include, for instance, the cyber augmentation of simulation that Professor Reddy mentioned, that include the cyber capabilities in design. And we'll see a few of those examples in the following points. Number 3, the challenge of the need to design competitive agents, algorithms, protocols, and models or architectures for better cyber collaborative products and systems to overcome resilience challenges. So we want to design better world around us. We want to design better assistive technology. We want to design the personal robot that will assist us. And this is a great challenge because in it is buried the mechanics of how do we do that? How do we bring it to reality? Number 4, the 3 opportunities, examples for challenges for emerging collaborative control theory augmentation. So if we're talking about these augmentations, let's be specific relative to manufacturing processes and to systems in general. First, the example of cyber collaborative production lines. All we have now are production lines that do not talk to each other, do not use machine learning to predict what will happen and try to provide elimination of errors, elimination of conflicts. So we know how to do that in certain areas. We have implemented it in certain areas, and it has been successful with significant results. But the challenge is how do we transform it to general industry and society? The other example is the cyber collaborative telerobotics and telepresence. We talked yesterday about the hub of collaborative intelligence. We have great opportunities and at the same time great challenges in order to bring intelligence that we already have. Again, I'm quoting some of my colleagues. Knowledge we already have and we are not using. So the next one is the cyber collaborative dynamic lines. We realize that in manufacturing, in healthcare, in education, in energy supply, and delivery, we have those challenges that things dynamically interact, and sometimes they go well, which we want, and sometimes they do not go well, in which case we need to provide the cyber capability to not only prevent them with machine learning and predictive models, but also to find out ways to overcome what has started to fail. So it has failed, fine, let's recover from it and let's prevent it from propagating to other dynamic lines that are waiting for more information, waiting for sharing of tools and resources. We can do a lot in that, and there is an opportunity and a challenge to innovate. And number 5 on this slide is a sustainable world and civilization depend on better, smarter, resilience, cyber collaborative production systems and the role of cyber augmentation with a question mark because it is a grand challenge. I will move to the next slide. And we talked about the factory of the future. What is the cyber support that we need for the collaborative factory of the future? So first, there is a value to the cyber augmented distributed e-work and robotics by collaborative control theory. There is a value. We need to understand that value. And as we talked yesterday with this brilliant question from industry, how do we justify and rationalize using this new technology, new capability, new cyber physical capabilities? How do we do that? How can we justify it to our management? How can we justify it to our clients? So this value exists. We need to measure it, we need to evaluate it, and that is a big challenge. Number two, cyber augmented collaboration models can overcome resilience challenges. Let's give some examples. Protocols, those are rules and procedures that are, first of all, agreed upon by all the parties that want to take part in the collaborative effort. So those protocols activate algorithms in order to optimize the decision-making of what is going on. They resolve conflicts, for instance. The protocols can negotiate agreements dynamically when things change and you need to agree. For instance, if you take the autonomous cars, or if you take water distribution or energy distribution and there are problems, or other negotiations for short-term and long-term supply and demand. So there are protocols, for instance, that have been developed for supply and demand sharing. Sometimes we have oversupply in one area and over-demand in another area. How do we share it in the sharing economy so that everybody can collaboratively succeed? And then we need protocols to prevent errors. That is a day-to-day case. We make errors all the time. We are late, we are early, we need to schedule, we need to negotiate agreements. Where do we meet? How do we go together to the airport? Then we need protocols for that are better outlining what is happening with cybernetic support. The next one, fault tolerance by teaming and backup control algorithms. So that means that if there are some faults in a system, mechanical system, software system, or embedded software in mechanical systems, there are faults and we have to tolerate them so we do not get to a failure. By teaming, we can do better and provide some backup, sometimes redundancy, and we need to control how it works so it works smoothly. And the next challenge, optimize sharing of resources, handling, transportation, and reuse. The optimized sharing we mentioned before. If you have tools and they are idle, why not share them with those that need the tools at the same time, and you can deliver it to them if you knew where it is. Number three, cyber augmentation by collaborative control theory enables distributed systems of systems achieve better performance and sustainability through collaboration. So we can realize that each system, we can design it for sustainability, but if we have system of systems, they can help each other, and this collaborative approach with cyber augmentation can make the resilience that we talked about part of the sustainability. Number four, hubs of industrial internets, short for the hub CI, enable collaborative intelligence to focus on augmenting human ability to collaborate effectively. So as we speak about collaborative robotics, devices collaborating with others, robots collaborating with others, as well as with humans, when we learn how to do that and develop such protocols, we can also improve and augment the way people collaborate more effectively. And finally, number five, smart automation means cyber augmented collaboration of distributed work. And this is a challenge that requires education. We mentioned several times that we need to think we're on the university campus and with industry. We need to train our workers better, and we may be able to talk a little more about that later in the statements. So this is where I would like to stop the conclusions and let the next speaker continue. Andrew?
Thank you. So, can you hear me? Is this good? Good? Okay. No slides, but I do have some thoughts and reflections as I looked at what we were talking about yesterday, and then also some of the comments that we heard today, and thinking a lot about sort of strategy and grand challenges. One of the things that has come across, as was talked about earlier, you can have a whole list of different grand challenges. And I think if you do samples in time or in different communities, you might get a variation in what shows up as actual grand challenges. But looking forward, I firmly believe that all of the grand challenges, the truly grand challenges that we're going to face as engineers and with our collaborators from other fields are going to reflect the human condition. The challenges that we face now are the same challenges roughly that were faced 1,000 years ago, that were faced 1,000 years before that, and are going to be faced 1,000 years from now. A grand challenge are things that affect humans, both as individuals and as a society. We're always going to care about health. Okay, you can write it different ways. It can be mental health. It can be health of the individual in terms of curing disease. It can be health of a population in terms of either infectious or non-communicable diseases. But keeping our population healthy is going to be a challenge, particularly as we get to, I forget how many they said, 10 billion people by 2050, with maybe a 25% increase in arable land. That's going to be a challenge. Energy. Okay, even though we've become more efficient, we are still always going to need energy. When we discovered fire, that was energy that we were using for something. Security and shelter. We're always going to want to protect ourselves, either from bad actors or from the environment. That's a basic human need, and we're going to need that now. We needed it 1,000 years ago. We're going to need it 1,000 years hence. How do we build, for example, if we look population-wise, how do we build mega cities as more and more people transition to the cities that function effectively, efficiently, with very little bottlenecks? I'm thinking about the bottlenecks just because of the drive-in this morning in Sao Paulo. Tied to that, mobility. Again, that was kind of the source of my discussion yesterday. It's just one of several grand challenges. We're always going to want to move from point A to point B. Our ancestors had to move to go ahead and get food. That is going to be no different. 1,000 years from now, it may not be food. Chances are the food will need to be mobile to come to us because we live in the cities and the food will be produced somewhere else. But that idea of mobility will always be a challenge. Similarly with food and water, communication. Some of these you may have technologies that underlie those grand challenges. Manufacturing could be an enabler to allow us to build shelter and security for ourselves. It's an interesting topic, but a lot of people don't really realize some of the big drivers behind manufacturing. There's economic drivers, but there's a very heavy tie to security. The countries that are able to build things better than anybody else are the ones that are able to play offense and defense better than anybody else. And that has certain geopolitical implications. It's no coincidence that different ages, if you look back in history, the Bronze Age, the Stone Age, those were tied to specific manufacturing techniques that were explicitly for security. So there's strong ties to manufacturing as an enabler. And I give these as individual elements, but really there's a lot of interaction between them. If I look at communication and information, I mean, that is now tied very closely to mobility. When you talk about connected vehicles and vehicles connected to the infrastructure or vehicles connected to each other, sharing communication. So the truly grand challenges, the ones that affect the human condition, one of the things I can predict with a great deal of confidence is that they will remain and they will become more and more integrated. The one I talked about yesterday was mobility, and I strongly believe that mobility and energy are closely linked, and electrification is going to be a trend that you will see as a means to enhance our mobility and energy needs as a society. It's going to have tremendous health implications as well, too, because you can address some of your conversion at scale rather than at the tailpipe, trying to convert or capture energy at a plant scale, a nuclear plant or a wind farm or solar panels. Even if it's a fossil fuel plant, you can actually do a better job of controlling emissions at the plant side versus burning fuel at an individual car side, because there are millions of cars on the roads. It's hard to make sure each one of those is operating optimally. But if you're doing it at scale in a plant and then shipping that electricity out, you can do a better job of maintenance and continuous monitoring and observation to make sure that you're minimizing the amount of emissions that you put into the air. As an example. Now, one of the things that I hope I got across yesterday is that meeting these grand challenges to address the human condition, because that's really when the challenges are grand, it's going to need multiple disciplines. We've heard multiple engineering disciplines and some excellent examples about bringing in economists and sociologists and psychologists, and I agree 100%. One of the things that we're going to definitely need, though, independent of the specific fields that are brought together to address one aspect of one of these grand challenges or an aspect of an interaction of multiple grand challenges, remember mobility and communication or energy and security, is that you have to be aware of, you have to take a systems perspective. You can't look at it just from a single subsystem of the overall problem. Even if you, I mean, it's hard to solve all of society's problems. If it was easy, it would be done by now, right? But moving forward, it's important to try and take a larger systems perspective, that whole elephant that we talk about. And even if you are not solving the entire systems problem, you're aware of the interactions of your system with other systems. Even if you don't necessarily solve that or optimize it, you're at least aware, so you know what some of the potential opportunities or what some of the potential detriments are going to be to the area that you solve. It's hard to do because that's not how we trained, as I discussed yesterday. But I believe that systems-type thinking is one of the ways we're going to make progress and start to bridge some of these individual disciplines to help us address those grand challenges. Two more points that I wanted to make. You saw the idea that was given at the beginning, the very beginning of this workshop, about energy and its time scale. Right? The time scale for changing over your energy mix roughly is about 50 years. Interestingly enough, the time scale for shelter, depending on your region of the world, in the United States, I think the average age of commercial buildings is like 50 to 75 years if you go to a major city. And so you're turning over your physical infrastructure for shelter roughly on that half to three-quarters of a century time scale, kind of sort of the same time scale as energy. Right? And so if you're going to make improvements to your any of these grand challenges, shelter, whatever, it's important to think about the time scale that you're operating on. Why? Because remember I said that many of these challenges to the human condition tend to be interlinked. Okay? You look at the communication. People will always need to communicate. Right? We're social animals. That's how we're wired. Okay? Communication and the means of information evolves on a much faster time scale than some of the others. I mean, 10 years ago, 11 years ago, we didn't have these. They just didn't exist. Okay? All right? And 10 years hence, we have the information of the world at our fingertips. All right? What will become very interesting as we move forward is to see how people are able to manage different timescales of evolution of technologies. Remember, 50 years for energy, pretty much 6 months to a year for information. Right? If I tie these together, okay, how do I manage that moving forward as these accelerate? Okay, that is going to be a challenge within a challenge. If you really want to address this from a big picture, systems level perspective. So I don't have the answers. I do know that there are very interesting problems out there. And I would encourage the talented folks of all levels of seniority to try and address those, but particularly some of the younger folks as we move forward. I'd encourage some of the younger folks that are listening or watching online, as well as the folks here in the audience, to think about that systems level approach as we go forward, looking at solving some of these grand challenges. The other thing I would say, and this is something that I've started to realize more and more as I've become responsible for larger and larger groups of people, when we start talking about some of these grand challenges, as I said, these are things that affect the human condition individually and as organizations. Okay, many of these, the things that we've talked about today, we haven't talked about pushing a plow. Okay, we haven't talked about lifting a heavy vat of molten metal to pour it into a mold. Nothing that we've talked about today has much to do with strength. Okay, mostly it's about what's up here. Okay, gone are the days where the physical attributes of the individual unit of human work, the person, mattered more than what's up here. And as we move forward as engineers, okay, since if ideas are the things that matter, I think it would be unfortunate if we didn't encompass all of our capacity as a society to address some of these challenges. The diversity in our teams is going to be important. And you heard us talk about diversity in terms of different types of engineering, or perhaps engineering and other fields, medicine. But there are other types of diversity. Looking around this room, I would probably say the diversity of gender is pretty limited. Okay? If you're looking for the best ideas and you want to go ahead and try and solve these in a very interdisciplinary way, I would think you would want to include half the population as we do this. Okay? And this is one of the things I've really started to realize as right now my research group individually is about half female, half male. There's a different type of interaction. There's a different type of communication. All right? And I would probably say more robust and better. I can give you lots of metrics if you actually want. And lots of people have done studies on this. And as we move forward and solve these grand challenges, I think it's important to draw in ideas from all aspects, gender, ethnicity, socioeconomic background, because we're looking for the best brains that are tuned to solve particular problems. So in order to do that, and get the kinds of ideas that the journal here, Politécnica, is looking to really address, I would encourage us to make that one of the things we think about in terms of the human capital development, because that's going to give many, many types of rewards down the road. Okay, and with that, I'll leave it and turn it over to the next speaker, Guiso.
I think that I'm going to repeat a little bit what I said yesterday. We engineered, we are very good as engineers to engineer the physical world, the more traditional engineering that we have been doing the last 100 years, building bridges, cars, mechanical things. But engineering, it's evolving. As I said yesterday, you are engineering body parts. You are engineering societies through examples as I gave as Facebook. And I think that we are stretching our capability of creating the science behind to help us. So engineering, it's evolving, and you have to rethink the way that you are teaching engineering, because the main classes that we teach in dynamics, statics, and those things are very designed exactly for that more traditional engineering. When you start engineering those different things that we are starting to create the world that never was, that I talked yesterday, using that idea, we really to create that type of world that we are creating today. I don't think that we are prepared. Other thing that we did, and this is really reinforcing what Andrew was talking, we used the idea of divide and conquer to solve our problems, to deal with complexity. You always divided the problem in sub-problems to be able to solve them, but you are never good putting everything together again. So you miss the whole elephant. You are designing the elephant by parts, and then we put it together. It doesn't look like an elephant anymore. So the idea is how you deal with that idea of dealing with the complexity. And I discussed this about the domino effect. And there is nothing that we can do in one way without affecting other way. For example, we are talking about energy. I hired a young faculty, Kelly Sands. She came from Texas. Her area of research is water energy nexus. Okay? So do you understand that? Just to have an idea, in California, the second biggest consumer of water is the energy sector. Okay? The main consumer of water is agriculture. And then is the energy sector. It's not us drinking, it's not our house, it's not watering our garden. Is why the energy sector? We need water to cool power plants. For every gallon of gasoline in the refining process, you think you need around 4 gallons of water. So all of fracking, you need a lot of water on fracking. Okay, you are pushing water through the system and to frack the soil and to get the gas and oil free. So water is extremely important in the energy sector. There is a lot of water embedded in the energy. Do you know who is the second biggest consumer of energy in the state of California? The water sector. You need a lot of energy to pump water all the way from the Colorado River to Los Angeles. You need a lot of energy to clean water in the water treatment plants. You need a lot of energy to pump water from the water treatment plant to your house. We need a lot of energy to clean the wastewater before you get rid of the water or you reuse the water after water treatment. So and again, people he's been talking about energy in a conference, talking about water in another conference, and no one is really understanding that you need more water, you need more energy, you need more energy, you need more water, and you are in a self-feedback loop that it's killing us. And not a lot of people talking. And then if you add food, agriculture needs a lot of water and a lot of energy. So there is a nexus: water, food, energy. All those things are the real grand challenges that you have to start looking. It's the interfaces. So how we solve those problems with the big picture, looking at the whole elephant. And this is something that we are not prepared. And I discussed yesterday about the silos and everything. If you keep working in silos, we are never going to work those things. If you fund research as silos, you are never going to solve those problems. But now comes my challenge as a department chair. If my generation cannot solve this problem, how can you build the next generation to solve this problem? So comes now the education. For me, one of my grand challenges myself is how we teach engineering, how you change the curriculum. You are facing a huge dilemma in engineering related to how you make the brick and mortar university relevant. Okay, I know that Andrew talked yesterday about, the human is a social animal. They really want to be on a campus, play football, go to a football game, watch the cheerleaders and have the fun. But for how long? For how long we are going to be able to bring the students to campus while they can have the same type of lecture online? If you keep delivering engineering with PowerPoints, and one-way delivery, we talk and the students listen, they can even come to campus, but they are going to stay sleeping in their dorm. And they are going to watch the video of the class later, and the students are doing this in the US. You are posting classes online, no students are showing up for class. If I'm going to wake up at 7 to watch you talk, I can watch later after a beer in my dorm. So how are you going to, so this is a big discussion in the US, how you, the teaching, it creates even a change in the physical way that you organize our universities. We are changing the teaching for lab space, hands, things that you cannot do online. You can sit in a lecture, but you really cannot go in a lab and build something, build a race car, or treat water with your own hands and in a water lab. So you have all the make space, things that we give challenges to students, and they go there and they build themselves. And this drives that what you do after with the idea of entrepreneurship. How we are going to get those students, if they are making things, how we are going to teach them to make things that are that they can sell, that they can make a startup. So all this is a new way of thinking about teaching engineering. That's a challenge that we have today. A lot of those things are done through curriculum. A lot of those things are done co-curricular. A lot of those things are done extracurricular. In the United States, you have a lot of competition. Every of our departments have mechanical engineering students are doing race cars and competing. This is extracurricular. In civil engineering, they do concrete canoes and steel bridges, and we have competitions. Aerospace engineering today is a big competition among all schools to see which team is going to get the rocket going farther into the space. So I think that USC was in the first place. I think that Texas A&M got the farther one last year. So it's all done extracurricular. The students are doing themselves, but the faculty is available. The faculty is full-time, it's in their offices and always available for these students to do those things and to help them to do those types of challenges and exercise. So this you have to rethink even the classroom. A lot of universities in engineering today are flipping the classroom. We don't teach anymore. We prepare the class online. We provide the materials, the readings, and class time is to answer questions and to do the exercise and to do the lab and to build things, and the professor is there to guide. So the whole idea of this type of lecture room, it's useless now. So you have physically to change the university to create the possibility of rethinking. So those are challenges that would make the new generation of engineers to interact. To, if they have a problem, they go to the students in business school. They go to the professors outside engineering to try to fix the problem. So if our generation cannot deal with those challenges, I think that we have to at least start thinking about how to build the next generation to deal with that.
Okay, I'll be faster because I wasn't prepared to talk today. Actually, I was prepared to talk earlier today, not right now. And I just discovered I was supposed to say something. Okay. And saying something of several important people saying important things is very difficult, right? Because they left very little for me to say that's important. So I'll keep talking about the elephant. Okay? Okay. Let's say, because...
Just have one question about that. You said those people are blind people? Blindfolded. You don't need to blindfold them. They're not going to see anything.
Okay.
That's
Okay.
our problem. We're not blindfolded.
I'll start continuing with the elephant puzzle. Okay. And because, first of all, in academic community, there is something bothering us. There is something disturbing that is bothering us, and we don't feel comfortable with that, and we pretend it's not there. And that's the puzzle of elephant is very good. The elephant is there. Introduced to him. That's what I said. Because when we got our degrees a few years ago, a few decades or something, I remember that I dreamed of doing something important for society. And at some point, we find ourselves concerned about publishing papers, more papers, and that's how sometimes we are concerned. We hire people thinking about the number of papers that they published. And I remember when I got my degree, I wasn't concerned about papers, I was concerned about doing something important. So that's bothering me is elephant in the room. So let's think that how we got here. So we talk about we need psychologists, we need sociologists, we need a little bit of history too. So let's remember about history. How we got here is important. And talking about the elephant is how the elephant got in the room. Okay? And let's understand how he got in the room so we can feel a little better. Okay. When we think about history of humanity and history of knowledge, and we see two branches of knowledge, the very old, let's say the ancient Persians, which supported technology for society or for war or whatsoever. So when we think about history books about who were the scientists in Egypt or in Mesopotamia, we don't know the names because knowledge was owned by the government. Okay? Then we have a second branch, which was a private supported from Greece that we are not necessarily concerned about the usefulness of this knowledge. We want to learn something. Okay? And let's say that these branches evolved somehow split over the 2,000 years. Then we got to, let's say, the Renaissance. Renaissance is a moment, a good moment, that it's impossible to have just two branches walking, ignoring each other. Let's remember that we do a little bit of that too. Okay. As engineers, we think that mathematicians don't do anything important. And mathematicians sometimes say that engineers don't know anything deep enough. Okay? So we are still living with these two branches. In my previous lecture, I was talking about this. We are not thinking correctly yet. So maybe we are still not thinking correctly and we are not prepared yet to do the right changes to address those grand challenges. That's why we need to change the way we think, the way we teach, the way we report our results. That's very important. Without doing that, we'll keep this knowledge split, which has been split for 2,000 years or more, maybe, let's say, 3,000, 4,000 years. So that's why I say, if the elephant's in the room, if we don't acknowledge its presence, we will not solve the grand challenges. And when I agree with Andrew, when he said that the grand challenges are there since early times. And people need to move around from point A to point B since early times. They walk it, then use horses, now they use cars, whatsoever. The difference now, they change the distance between point A and point B. And that's what's beautiful about that. The point is that what's different from those challenges all over is that now they're more complex. At early times, maybe those challenges of going point A to point B, one person was able to solve it. Now, probably to solve this problem, we need the mathematicians, we need the physicists, we need the engineers, we need the sociologists, we need the psychologists. It means that we must stop thinking that what the other people does is not important. We need to start recognizing the relevance of human knowledge. Stop thinking about science and technology or science engineering. We must start thinking that as human knowledge, as unifying the knowledge with that perspective. That's, for me, is the key point to start addressing the grand challenges. Okay, so, and I only use one key word to finish my talk. And the key word is efficiency. Efficiency is the history of humankind. Societies survive when they do better than other societies. A technology survives when it's better, it's more efficient than other technology. Okay. Our history is challenging efficiency. So when we think about those grand challenges, we must think about how we do better. Okay. That's how we are going to survive. So I leave here now for our discussion.
Well, it makes it even more difficult for me to continue this conversation. But anyway, thank you all for bringing these statements because, again, you complete one to the other. So we have in a good situation to start this debate. Does anybody want to have a question or should I suggest a way to? Please, Professor Emilio.
Okay, so I have two topics here. That first one is for Professor Reddy. So yesterday in your presentation, interesting question regarding challenge raised. So when you talk about modeling, like the traditional way of modeling, like structures and so on, is using mechanics, theory, and so on. But there are other scientists, they like to use like big data information to model structures, like Lucio knows very well. So how do you, like I would say, we have these two worlds, right? When it's based on the physics of the law, physics law, constitutive equations, and so on. And then you have this other world where they say, no, listen, we know you have this system here, could be a structure, could be a, I don't know. And then we have lots of data about how it behaves. So I also can model it. And so, I mean, how can you put these two together? How do you see this? This is my opinion. I mean, how they can aggregate them. So this is my first question. Then I have the second one.
It's on. So, no. Yeah. So it really depends on the problem, how you bring the data and also the principles of whatever that particular physics is. So, by the way, electrical engineering may have different principles and laws. So the combination, see, most of the data is really constitutive. That is where the major issues are, because materials, not like metals. There are a lot of different materials which exhibit inhomogeneity, heterogeneity. So it is very difficult problem to analyze, and that is really main problem with whether it is a earthquake or any tsunamis, because of the material data is so different. What happens in one place, one country, is not exactly the same thing. You may learn something, but the data may not be valid. Okay, so it has. So you don't want to wrap whole thing into one. It has to be focused, means problem dependent. And so the machine learning is going to only do that much. It cannot. It can only find generic trends. Okay, so we have to validate. I mean, in this case, I'm using validation in a different context. Validate with the laws of physics or laws of that particular problem. And then you go from there. Otherwise, if it is only, the data, trends, and if nobody checks if those trends are correct by using an independent verification, you won't be able to get right results. So that is how they have to interact. Okay, so it is definitely problem dependent. We cannot just come up with a general idea. Although machine learning folks think that they can do anything as long as they have data. So I'm trying to propose that you have to have a physics-based modeling. If you don't have that, it's like mathematical models you can construct. How do you know that they are representing the physics of that problem unless you have validation, independent of validation through experiments? Right? So that is really what I'm trying to say.
Can I say something? I completely agree, and I believe that anything with data is domain specific, and this is why I think that my research is important. Computer scientists cannot do my research. They know the machine learning, but they don't understand the domain. If you think about predicting behavior of a bridge, if you add sensors on bridge, if you want to make a smart bridge, try to get a computer science to analyze the data coming from the sensors. They have no idea. They are never going to link the sensor output with a problem in the bridge. Okay, they don't understand the behavior of the bridge. A very simple example is you can get from data a huge correlation of Diet Coke and obesity. Okay. So you are going to say that people are obese because of Diet Coke, or they are drinking Diet Coke because they are obese. Okay? The data, it's never going to tell anything. It's just going to find correlations, but you need to have a huge understanding about the domain to be able to make sense of the data. So it's extremely important today to teach data science to our students. The evolution in data science, in machine learning, it's not going to happen from computer science. They are going to write algorithms. They are going to say, they do research if someone is smiling or not, face recognition. So those kinds of things. But as soon as enter an engineering problem, they won't be able to do anything unless you understand the domain that you are looking at the data.
Yeah, one thing too, I think one of the things you're getting to is, so I agree 100%, it's a sort of domain specific, and knowledge of the domain will help a lot in understanding what the data is saying. If I understand correctly, you're wondering, is there a use case for trying to combine data-driven and model-based? I think there are. I think there are some examples where that's done very effectively. If you sort of remember what I was talking about yesterday, where I took up a relatively complex system and decomposed it into individual functions. And in each of those individual functions, you can represent some of those functions. If you had to do a model, you could represent some of those functions with a data-driven protocol, and some of those functions you could represent with a model-based protocol. A very good example that is current right now would be autonomous vehicles, autonomous cars. You hear a lot about this. So if I functionally decompose the autonomous vehicle into different aspects of it, the scene recognition in terms of the environment and what is going on, and is that a dog or is that a bicycle? Is it a tree or is that a person? A lot of that, it's very hard to model with first principles, but you got to get the car on the road because all your competitors are doing it too. So I got to take a data-driven approach to that. And I've got enough data, drive around a bunch of cars, do the data-driven. I pass that information now to what my car has to do. And I know a lot about my car. Right? I can do a model-based decision-making control, figure out what my gear settings are going to be and what my steering is going to do, because I know exactly how that car is going to perform. It becomes even more important in emergency situations. I got to know exactly how that car is going to perform because I probably don't have enough emergency situation data. So that's sort of one example of where you take sort of the data-driven where it's appropriate, as long as you functionally decompose the problem appropriately so that you have right information interchange between the two, and then you can have model-based somewhere else, and you can solve the whole problem that way. And there are many other situations where you can actually do that as well. In building systems for energy management, they'll do a lot of a combination of occupancy, prediction, and some of that will be done sensor, some of that will be done model-based, some of that will be done data-driven, dependent on the particular problem, as long as you can represent systems appropriately and then link them appropriately to come up with a super system.
I cannot resist also participating among my friends. I want to defend my good colleagues from computer science and statistics that are focusing on machine learning. We all know that the names keep changing because of conversion and diversion. So machine learning today used to be called pattern recognition, and pattern recognition used to be called data mining, and the name is not important. We should also be positive on our achievements. Machine learning is saying if we know how the past behaved and we can use it statistically to draw from good knowledge to prevent repeating mistakes, then let's do that. But there is a bigger thing here. What we don't know, we don't know. This is a very important principle for all of us, because we didn't know about the internet or the cell phone before they were erupting and disrupting social activities, commercial activities, economic activities, and so on. Now that we have them, we don't say we solved everything. We realize as humanity we have challenges all the time, but at the same time we have major progress. Machine learning and data mining and pattern recognition have brought us a long way in being able to prevent errors from happening. But that brings us to the Politécnica approach or multidisciplinary approach to solving grand challenges, and that is the issue of sharing. It has been said several times, the knowledge we have in disciplines, say about bridges, the knowledge we have about machine learning may not reside all in the same team. But breaking silos means the purpose is to share the knowledge and the expertise that is incomplete in each of us, in each of our disciplines. And when we work together, we can do better. And our only chance for the grand challenges of society are to share and do what we call augmentation. We will do better than the sum of our knowledge if we take collaborative intelligence for multiple knowledge sources, be it machines, be it sensors, and of course, be it humans. And the humans can be experts or novices. The novices can bring us intelligence that is not influenced by previous learning and is original and creative and disruptive. So the diversity that Andrew mentioned before is the diversity of new ideas, not necessarily always coming from children or from people with no experience. Sometimes it comes from experts. I can tell you that just sitting among colleagues who are smart and willing to share, you immediately create new innovations. You have new opportunities for solutions. So while we present all our big challenges, big problems, grand problems, we also have to realize that we have great opportunities by sharing and by collaborating. We cannot all do it as humans. We cannot always be co-located. We cannot always have the time to do it because we have other commitments. Hence, computer science and computing can help us with big memories and statistical learning to do the best that we can with what we have. We're not saying that we will see the corners. We will not say that we can use the past knowledge in order to predict everything that happens. But if we predict only 90% of the problems that we have and prevent them, that is already a big achievement. So to summarize, credit to our statistics colleagues and our computer science colleagues that are helping us to see that we can leverage what we all know, try to collaboratively, cumulatively put it together, and then try to solve big problems.
You have a second question?
Yeah, I have a second question. Actually, it's for any of you. Let's talk about education now. Okay, so you guys have been talking about the SIOS, right? So, of course, it's definitely from the speech, from the talks yesterday and the discussion today, these multidisciplinary issues, they are important. Now, let's talk about diversity of societies, cultures, and countries. Okay, so all of us, we have traveled around the world, okay? We know many countries, and sometimes we go to museums, and so, for example, we see engineering solutions that, you know, like I was with Professor Reddy here in Brazil, we have a computer in our car. When you go to a parking lot, it just charges automatically. So I don't, like in US, I have to go to a machine and buy a ticket to, right? So, and then you go to, I don't know, Europe, you face other interesting solutions. And even if you go to a museum, you see the ancient people, like for example here in Central America, Latin America, you see those Incas, Mayas. Till nowadays, we don't know how they build, we don't know how to build those pyramids and so on. So what I'm going to ask is the following. How do you see from the students' perspective the importance of getting in touch with other cultures? Like, so we are talking about SIOS, not all of now multidisciplinary SIOS, but we are talking about cultural SIOS. So let's say a student in US says, oh, do I have anything to learn if I go to Brazil or Europe or Central America or, I don't know. So how do you see, now thinking about education of the students, how do you see how good it is to have this diversity from, now think about engineering point of view, not only engineering solutions, like we see interesting engineering solutions in all societies around the world, it doesn't say. So we see different solutions, sometimes the same solutions adopted here in the other side of the world, or sometimes different solutions. So how do you see, how important do you think it's for the students to have this, you know, diversity of know other cultures and societies and so on? So,
can I? Well, this is something continuously changing. Okay, even NSF tried to support curriculum changes, things like that, you know, to make the education more broader. But you know, there is a big problem. There is a resistance from parents. See, we used to have 143 credit hours way back maybe 10 or 15 years ago. Now it is reduced to 120. So where are these? And then on top of it, then you ask these students to go take courses in sociology, psychology, because you want to broaden the education. So these are all good things, but then you cannot go on cutting. Then what happens is they don't learn enough of the professional tools. I mean, in whatever they are measuring in, right? So this is not going to be settled that easily because it has other forces working against, which is because the parents wants to save money, tuition they have to pay. So I'm not going to sit here and talk about socializing education where, you know, parents don't have to pay fee. Like many countries, actually, they don't. America is probably most expensive. Okay, so but the thrust here is we still need people to specialize. Okay, so don't get me wrong there. We want them to have this broad background in terms of understanding the fields. Okay, but we cannot make it too broad either. Okay, so there has to be a focus. I mean, by the way, anything we study, there has to be a focus. And focus dictates, when we talk about the data mining and physical understanding, is problem dependent. Right? Whether you study a bridge and tsunami, earthquake, or a car, they're all different. Right? The data is different. So you have to be focused, and then it's a problem dependent issue. So coming back to this education, I really like to see there are no walls. But you cannot make it, only can make it transparent, not remove totally walls. Because what happens is the students or people won't learn enough of their own field. So we have to also guard against diluting the focus of learning tools of their profession. Because they are required to use those tools when they go to work, right? So it is, in summary, I don't have a solution because this is, various forces are working, some of them are working together, some of them working against this interdisciplinary thing. In fact, there are a lot of political aspects also. For example, if a faculty member works with other departments as collaborative grants, then when it comes for tenure and promotion, then they say, oh, this person is not contributing enough to this department. So we will only divide by this. See, this kind of thing happened, but it's slowly going away. But I think faculty has been subjected to penalizations when they worked with other people. So in fact, this is one of the critical things that we are discussing always, saying that this should not be. In fact, if you double dip is okay in these cases. That means the person other side should get authorship of that fully, and person on this side should get authorship of fully. If the two of them collaborated, they should not say 0.5. So anyway, this interdisciplinary thing is not as simple as it looks in terms of enforcing it. Okay.
Just 1 second. But your question was a little bit different. It was about study abroad. Yeah. So look here. You have 4 faculty here, okay, from the U.S. 1 from Brazil, 1 from Jamaica, 1 from Israel, 1 from India.
Yeah.
So the reality in the U.S. it's very different when you think about exposing students to different cultures, different things, from the classmates to the faculty. And Brazil, it's a completely different reality. You are all Brazilian professors with all Brazilian students. So that's a bigger problem here. Okay? But still, study abroad, it's a big issue in the U.S. And it's a problem in engineering because normally the students start at the university, they try to feel comfortable in the university. And in the first years, they are taking many of those what you call general elective classes. They are not the really core classes in engineering. And those are the classes that are easy to transfer if they take a class somewhere else and then they come back to their university. And when the students in the US, they start feeling that they are ready to go abroad, it's when they are taking really the core courses, that are the courses much more difficult to transfer. So a lot of universities are trying to start educating the students to study abroad as early as possible because that's when they are not going to delay their graduation because they can transfer the credits. We are working very hard on that. But there is another issue that's a big problem in the U.S. that's different than here. The majority of the students in the U.S., I make a joke, so you are all Americans, but you can make joke. I say if you speak 2 languages, you are bilingual. If you speak more than 3 languages, you are multilingual. If you speak 1 language, you are an American. So the issue is that majority of our students don't speak a second language, and the majority of our students they study abroad in English-speaking countries. So, and then they are really not being exposed to the culture. So there are issues in the US, but I think that this is a bigger problem in Brazil that you're going to have to face and fix it here. The other issue that a lot of study abroad that the students are doing is extracurricular. You have a lot of interesting things that the students go to third world countries where the Engineers Without Borders, and they go for a smaller period, and they go to understand problems and solutions in different countries, not in the classroom settings. So there are a lot of options, but I think that's a bigger problem here in Brazil because of the characteristics of your students and characteristics of your faculty.
And following on that, I'm actually pretty optimistic. I think the first question was how important is the cultural background, and sort of what do we see as the future? I think it's tremendously important to have a cultural IQ, if you will, for our students, because they may end up going to work in Greece or China or
yeah, that's my point. Okay,
when they graduate.
I mean, just sorry, continue. And then.
Oh, okay, yeah, and we realize that. At Illinois, one of the things we did was we made a conscious effort to increase our international student base. So right now, about 20% of our undergraduate population is international. And I think I'm a realist with a tinge of optimism. I think I'm hopeful for the future because if I look at my own kids and their friends, you know, they because of globalization, they're aware of globalization, much more so than I was when I was their age. They get online. Much to my chagrin, they spend a lot of time watching people play video games, for example, but they're watching people from Nigeria, a team play whatever the video games are that they play now. They have these competitions and leagues. I don't fully understand it. Or people from China or people from Australia, and they're aware that there is a world out there that's not just Central Illinois, and they want to participate. So they actually seek out a lot of these opportunities. When they come to college, they're looking, you know, how do I do study abroad? Because I know it's something, not just I want to go and party in Ibiza or something like that. It's because this is going to give me a competitive advantage when I get out of here and have to compete against everybody else from across the globe for that job at Exxon, for example. And I see it flows down. So I see it actually in the high schools. My first son, he's been to Japan twice. Takes Japanese. He likes the culture. He speaks Japanese now as a high school student. They've taken him on 2 separate occasions to spend time staying over there to host family. That's almost like a study abroad. It wasn't anything that the parents pushed. It's something that he said, this is what I want to do, and it was through the school. They said, okay, yes, we'll support this. For them to do that. Other kid has gone for sports-related things to do international stuff, and they're building that type of culture in. And the students that I see coming to university within Illinois have a much greater cultural IQ and understanding and experience set than 25 years ago. And so I'm actually hopeful that we're heading in the right direction.
Yeah.
Are we far enough? I don't know. But I think we are heading in the right direction.
Just like what you said, okay, we have many agreements with some U.S. universities and European universities. So we send many Brazilians abroad, but you don't see Americans almost here. So it's not like you said. So, I mean, when we talk, about to say international diversity, the fact that you guys are in U.S. and you are foreigners there, it's okay, but it's different. I mean, it's still the American culture, right? So I'm saying, I'm not talking about the United States. It could be Europe too. So I say, like Andrew said, when the students, they come here or they go to, I don't know, India, whatever, it's different, right? So how important is this for the education of them, like to know this? I think Andrew more or less got my point. And that's my question. So we don't have American students coming here. Doesn't say but we have the Brazilian students going there in the sense that, you know, a lot. And so, I mean, we have Europeans, Brazilian goes to Europe, but we never do this exchange. It's difficult to match. I'm just saying that the students, looks like the vision of the students is that, there's nothing to see there. That's what I'm saying.
So they do travel abroad. As I said, the majority goes to English-speaking countries.
Okay.
In engineering, even more. But you have, for example, I know that USC students come a lot to USP in the business school.
Yeah. So let's give the opportunity. We have another question there.
You want to say something?
Okay.
May I say
Sorry.
Emilio, may I say something? Sure. Or did you get full answer?
Please.
I just wanted to combine some of the wisdom from the previous answers to elaborate on your question. Education is extremely important. There is no question about it. But I want to look a little backward. Some of us sat on such panels years ago. And I remember the same issue of multicultural globalization. How is it going to influence education? Will Chinese take over the interchange of globality and so on? So those questions are not new. Also, there was a big concern in panels years ago about the influence of computers. That was before Internet, the BI. Before Internet, we already had panels talking about what will happen, the influence of computers. And everybody said the positive thing is less reliance on memorization. So we don't even realize that. But the way we teach now is not relying on rote memorization. We are expecting the students to be much more agile. And we already talk about millennials and Z generation in our students coming into classes, and they are very sensitive to global cultural exchange. And some of them don't come, as you say, but those are people that are not interested, at least in this stage of their life. But they all are, through the internet today, sharing, participating, learning, and they learn very quickly. So the challenge of memorization or not in years ago education has already been solved. The exchange issue is still there, but I don't think, as my colleague said, it is a choice of the students. They may prefer to go with a family to visit Italy and learn Italian, not through the university. And a lot of what we're doing today, and even preparing our education, is for online courses, partially, realizing that the specificity is very important. And one thing that we used to say on panels, and has not yet been mentioned, is the hands-on experience. Very difficult to get hands-on experience on internet. The advice that Lucio gave us is breaking the silos, and all those competitions, multidisciplinary competitions are, if the students don't like to do hands-on learning, they have the competition, and then they really have to build something. So when they build something, and it could be a mathematical competition of algorithm development, who is going to develop the fastest app to solve a problem, this education is changing the way we are educating and planning our courses. I may have gone a little beyond your question, but I think it is all important. There is one more thing I want to add, and that is something I hinted yesterday. We already said in previous years, previous generations, and we keep saying it in the new generations, we have to teach students to learn, just as we learned how to learn. And the cycle of knowledge truism or truth is changing all the time. The diversity of knowledge grows so quickly, but at the same time, the technology to access that through remote memories is also increasing. So what we see is that we have the approach enabling students to learn a lot by themselves. And we see that even in our classes. When they sometimes listen to something else, it means that they have a way of parallelism, and they can listen, maybe not as well, but they can listen to the lecture or to other students presenting homework, and at the same time learning some other things. So there is definitely change, and we are not able to do exactly what the next generations are able to do, and we have to hope that they will be better learners than us. Thank you.
Okay. Do we have another question there?
As we discussed here, a different education approach is necessary in order to build an engineer, to have an engineer that can see the big picture, the elephant as a whole. Otherwise, however, we have education going to a total different direction where the students are becoming more isolated, just absorbing the knowledge through the distance learning tools. There are courses that are fully distance learning courses now. And how can those things converge together? That we need more contact, more interaction in order to have professionals that can understand the entire problem, and education are going to the different directions. How it's possible to match those things?
Okay.
A little bit, and there's sort of a follow-on to that. We talked about that transactional knowledge versus the sort of collaborative. The interesting thing is, sort of when you go for, as Professor Reddy said, you sort of need that disciplinary depth. Many of the folks that are looking to do the online courses, it's not like, I mean, there were some discussions about people that are on campus and they just choose not to get up early. But that's not the majority of the people that do the online courses and the online education. Most of the people that do the online education, they tend to have constraints. They're working full-time, and so they can't go on campus. That's where most of the online MBAs come from. It's a sort of a evolution of the executive MBA. And so it's a matter of priority, right? Given the constraint that I have, that I can't relocate physically to be there, right, this is the best option that I have to get perhaps greater depth. A way to meld that would be if they're working in some organization, let's say they're working at Embraer and they're doing fluid mechanics, is they could go online and take a course in management or collaborative team building or something like that, and get that bit of broadening to them. But they're going to be constrained by their physical location. So it's going to be situation dependent. You can actually do it very nicely if folks are on campus, but I understand that is a small portion of the people that get educated in this world. You have a little bit more flexibility because you can actually do the flipped classrooms and the blended learning, and also introduce some of the broadening modules as extracurricular learning. I think if I understand the gist of the question, how do I take online learning and get that broad experience that allows me to see the whole elephant? It may be a little bit of trying to solve an over-constrained optimization problem, right? And you may have to figure out which of the constraints you want to relax. It would be hard to get somebody working in a remote area on an oil rig, a team-based, collaborative, immersive experience online. That's just a fact. Okay, so you may have to prioritize in those situations. Each one is dependent, and figure out what's most important. If the team-based collaborative exercise is most important, that's where you'd need to have some type of synchronous activity with your colleagues. You could do the synchronous stuff online, or you actually bring them to campus for short periods of time. That's what they used to do for the executive MBA. But I think it's going to be a little bit of a challenge to solve an over-constrained problem, to say that we're going to be spatially non-collocated and asynchronous in time, and get both a deep knowledge as well as the immersive, collaborative, team-building type of environment. That to me seems like you're asking for a bit much. A little bit of an over-constrained optimization problem. You figure out how to prioritize and figure out which pieces are most important. Right? I think the student that wants to get those could then figure out how to go ahead and apportion their time and location.
Okay. Well, I think it's up to me to present a challenging question. So, since we are talking about big challenges. Well, summarizing all you said, all of you, we have to separate the question in 2 points. How to face the new challenges, how to prepare people to do it after we are done. So, I will borrow a model that comes from US, from NASA, who says that if you want to prepare people to solve a problem, be it very well-trained technicians and scientists or students, you have to work in three directions. They call the model ask. A from attitude, S from skill, K from knowledge. Seems to me, I don't know if I'm right, that we all focus on knowledge only. So if you're talking about students, we are talking about building new curricula and everything. If we are talking about scientists, going to the silos, to the areas, going to experts in that area. But the big problem is not like that, like Professor Justo said. So problems do not select areas. Problems do not have preferences. So we have to face a problem that was not prepared the same way we prepare ourselves. So the question is, being valid for scientists or valid for students, what are the attitudes we have to change? And what are the skills we do not have so far?
No, that's why I stepped out. I have to answer that one. I knew he was going to ask a tough one, so that's why
I think that the skills is very related to problem-solving skills. Okay, that it's missing the way that you taught before, and I agree. The idea of learning to learn. If you create these skills for them to learn how to learn, so you don't have to give them knowledge; they can absorb the knowledge to solve the problem. And if they know how to solve problems, so you are giving them the capability of dealing with those types of things. And this, I believe that it's done by doing the hands-on teaching, more problem-focused teaching, where you have the students and you drop them to the problems and they have to go after the knowledge by replicating the way that you solve problems in the education settings. Attitude, it's much more complex. But again, what you try to do to deal with the attitude is exposing them to multicultural and multidisciplinary teams. And this is exactly the reason why iPodia was signed from USC with USP. It's the idea of teaching the students. The class that I taught with Vanderlei was a problem-driven class where the students had to work on assignments, and the groups had 2 students in the US and 2 students here at USP, and they had to work the problem together. I think that by creating and replicating the way that the world works and having the students to deal with that, they have to learn the attitude. By working with different people with different backgrounds and different culture. And this comes that Andrew was discussing about diversity and all those things. We have to map and design that experience to our students and to expose them to all those kinds of situations, and then we will allow them to know which attitude and how to solve those problems, because they are going to be exposed as a student.
No, I don't know the question, but I did want to hit on just one thing that you said, because I've heard it echoed a couple times, and I want to make sure that the point that I was making earlier today when I was at the podium is clearly heard here and online. When I was talking about diversity, there's the diversity of areas, okay? But there's also the diversity of types of people. The gender diversity. I noticed there are no women in the audience sitting here. That's half the population of the world. As engineering, shame on us if we're looking for the best ideas and the best people. Study after study will demonstrate. There was an excellent faculty member from the University of Michigan that did studies on this that showed how well-organized and well-managed diverse teams consistently outperform homogeneous teams, and the data is there. It's interesting, poorly managed diverse teams significantly underperform homogeneous teams. Homogeneous teams tend not to move as much with respect to how they're managed and interacted. So to capture a lot of the benefits that I was talking about, it's not just diversity of areas. I want that to be very, very, very clear.
Okay.
I just want to repeat the question for the benefit of Andrew, because the question was worthwhile to mention. And if I understand correctly, Professor Reinaldo is asking, first of all, is it just about knowledge that we have to teach or learn with our students, and how do we prepare them, the second part, to use this knowledge or to address the challenges that we looked for the knowledge of the challenge, understanding the challenge and understanding in a multidisciplinary way. So I fully concur with my colleagues here. I would say that the good signs that we see is that when we ask students for senior design courses to start a team, we have a Korean team, a Chinese team, an Arab team, we have all those teams, and then of course we have a small protocol. You cannot be from the same culture on the team because we force the diversity. When we have the engineering video streaming courses that are taught both on campus and off campus, and we have teams that have to do hands-on projects, then we have a small protocol. You must have in the team of 4, 2 from industry and 2 from on campus. And we have indeed found that it is not theoretical. Diverse teams, heterogeneous teams are always stronger, better in their performance. So this was just a nuance or caveat on once we know the challenges, whatever we know knowledge, of course it's a challenge because we don't know all the knowledge. We have teamworks. We begin with small projects with the students from first year, and then we grow the challenge and even go to grand challenges in the senior design kind of projects.
Okay. We have a technical problem to accept questions from the internet now. Right now, I apologize for that. But just to direct your final statements, I just to pose one thing more. The idea of my question is, I think what is missed just for researchers and for students is how to compose different perspectives. It's not possible to have all the knowledge, not for us, not for our students. So what we have to face this new challenge, to know how to compose the perspective of a mechanical, the perspective of a computer scientist or industrial engineering, the perspective of electrical engineering, civil engineering, and everything. So seems to me, I don't know if you agree, we don't know very well. We are learning, we are evolving on this, but we do not get to the final point and composing those perspectives. It's exactly this perspective that is going to give us the condition to face the big challenges. That's.
I agree, and now that I understand your question. So I think it's a challenge now. I agree. One of the best things that we could do, looking towards the young people, is get them excited. Get them excited about the grand challenges. I don't know if you remember the space race. Mm-hmm. You know, going to the moon, right? Going to the moon, people came. It was a vision. It was something that humanity was going to come together and do something that we had never done before and solve a problem. And you saw people from many different backgrounds come together to help achieve that goal and that vision. I think somewhere along the way we got a little cautious. I think we decomposed the system problem into multiple subsystems, as my good friend said. And I think in our instruction to our young people, we haven't spent as much time putting it all back together to say, here is the way that we are going to, as engineers, change the world. Here's how we're going to make it. Here's where we're going to matter. Here's where we are going to write history. Okay? 200 years from now, they're going to talk about us because of X. And you put that idea into several thousand kids' heads, right? And maybe not all of them, right? But if 10% of them say, I want to be the one, they're going to go out and find the team, right? You're going to empower them to find and every time they stub their toe and hit a roadblock, right, they're going to figure out a way, what they need. They may not have everything at the beginning, right, but they're going to figure out what their need is and go and find the resources they need to make it happen. I think that idea of engineering as something that is visionary and exciting and again, changing the world, we've lost a little bit. And if we can get that back into the heads of the people that we train in the next generation, I think we'll be in a pretty good situation in terms of having them pull. So instead of us push to say you have to have one of these, you have to have one of these, you have to have one of these, right? You put the stake out there and say, this is what you can achieve when you grow up. You can be that, and have them pull some of those ideas towards that.
Okay. Does anybody want to make it?
And I never understand why. You see, even in TV shows, you have TV shows for medical, lawyers, and all those series on TV. You don't have anyone. You had MacGyver in the past that would that would those things. But what happened? We are missing something here as engineers and getting people to see, oh my God, that's cool. I wanted to do that. And I don't understand. There are so many interesting and cool things that we do. You are missing. USC paid to create a female MacGyver engineer show, TV show. So they made a competition for people to write it, and it happened, but ended up not being syndicated. They did the 5 or 6 of those shows, and the TVs didn't buy it. So why? I don't understand.
I mean, I'm going to only comment to that. See, the ingenuity and creativity is nothing to do with your education. That's totally. What you, after those ideas come from a crank or who, even uneducated, engineering the idea is where education helps. So MacGyver thing is more of his ingenuity. Okay? So that cannot be taught. Right. So the creativity and ingenuity to large extent more natural to genetically coming. So then of course you can enhance those through education. Okay? By creating, examples of, giving something in play. So for example, if you take, we call engineering 101. It is really a babysitting class. I taught it. So what it means is we give them Legos, okay? Ask them to do all kinds of things, okay? Create, a mass that is going to travel fast, or the smallest mass, create all those objects. Just make them play, and or wooden construction sets. So we make them to think. That's what it is, and we also teach a little bit of programming or that. But that is a class where it is almost like you can do that even in middle school and high school, right? See, by the time they come to college, it's a little bit too late for us to mold them to that much. We can create more opportunities in terms of tools. But changing their mindset, I think, is a bit late. It has to happen earlier than college. So in this K-12 or whatever they call it, K-1, yeah. So that is the most important to any society. That is where you have to invest. Unfortunately, we are not doing. Those teachers, we were talking about in the car, if the school in Beverly Hills has to have very good teacher there, they have to be paid enough so that they can live nearby and go there, right? So you don't expect these teachers with those meager salaries to live in those areas and do their job. So, this is just a comment, but I think, it's really complicated when it comes to, that kind of thing. Creativity, is not really being, we cannot teach so much.
I'll give one example of, two examples of one person, of the kind of people that I'm looking to that we could unleash as engineers. So Elon Musk, love him or hate him, right or wrong, okay? There are things that he's done well, things that he's not done as well. You look at what he has done through sheer force of personality. You could not have cheap access to space. Okay, you could only have 6 launches a year. That was the line, right? And they would come out of Vandenberg, or they'd come out of Canaveral, or maybe Russia or something like that. Musk said, "No, I want to colonize Mars. I want to colonize Mars. That's going to be my legacy, right? I'm going to have a cheap, reusable rocket." You can't do it. All the NASA folks said, "You can't do it. It's impossible. We're engineers. We know you can't do it." They limited themselves. He was a visionary. He said, "Damn it, I don't care. I want to make this happen. I think we can do it." And he inspired people. You know the number of kids that come through that want to work for SpaceX? All of them do. And when you go to SpaceX, right? Again, right or wrong, this is not an ad for SpaceX. They work insane hours. I have been there, gone there. You go there 8 o'clock at night. Half the engineering staff is still there because they're driven. Partly they're driven from above, but also it attracts the kind of people that want to buy into that dream. They do have a lot of, the cafeteria is nice, yes. But they buy into the vision. You get a lot of these starry-eyed kids that go in and buy into the vision. Autonomous cars. Oh, you can't do it. You can't do it. Or electric cars, sorry. General Motors came with the EV. Do you remember the EV1? They had an electric car on the road. When Musk came out and said I was going to do an electric vehicle, everybody said, "You're full of it. That'll never work. That'll never work." He sold a vision, right? And when he sold a vision, you know what he sold a vision on? Everybody's like, "Oh man, we can do this thing. It'll be really, really efficient. It'll be green, save the planet." He said, "Nah, I'm going to go 0 to 60 in 3 seconds. I'm going to have the highest performance. I'm not going to go after efficiency. I'm going to go after performance and luxury, and that's going to define that market." Right? I'm going to start at that part of the market, and then maybe I'll drive down. Right? And that changed the game for electric vehicles. Now, from what I understand, Model 3 and Model S last month outsold every other sort of luxury car in the world. And a lot of people want to go work for Tesla, right? Because it's cool, because they can see themselves as part of this vision. I want more people like that. Right, that's solving a mobility problem. If it happens to be, there are lots of security problems that the assured access and cheap access to space will solve. It will serve certain societal needs, right? And I want more people like that to harness, and they're multidisciplinary. Right? There are lots of different disciplines that you take to do that, from additive fab. They use a lot of additive fab in their rockets, interestingly enough, to allow some of the refurbishing and turn time. Where are more of those? Where are more of those that are going to pull people together and go after some grand challenge, some grand vision? We don't train them. We tell them it can't be done. Right? I've heard people say, "You can't do that." And I heard them criticize him when he was coming up. Why do we do that? Instead of saying, "Yes, you can," to use a campaign slogan from a few years ago.
That is attitude. That is attitude.
That is what?
Attitude.
Yeah. We need more of that.
Can do anything.
Okay, we have come to the end of this panel, so I will ask you to do you have a question? Oh.
Only one link. I'm an engineer. Well, I'm an engineer and economist, both schools. I'm teaching in business school. Probably the biggest challenge is inside. For example, during the process in the business school, when I tried to do something different, and the guys, my colleagues, told me, "No, that's an executive view. You need to have the business school view." Oh, sorry. For me, the same thing. The same happens in engineering. Our background is constructed to think inside the box, to work directly in a problem provided for fix. Why not think bigger? Why everybody? That's not possible. Try the basic things. And sometimes I agree. I fully agree in thinking big, in working bigger things. But sometimes I fall in my background and it's not the time. Why it's not the time? Maybe the biggest challenge is, okay, you stop, there's a big problem because the trend is collaborative, the economy change, is do not buy, is share, is a link for all this.
Yeah, but you know, it's I don't completely agree with that. Thinking as a researcher, I never start a research that cannot be done. Okay, as researcher, we are very used with the idea of challenging the status and saying, okay, come with a complete crazy hypothesis, and you go. If it doesn't work, you negate the hypothesis, but we go and do it. And again, I don't understand how professors can be forward-thinking when they are doing research, but when they discuss curriculum, they really cannot do it. I don't understand where the switch in their brains work and that they change the mode of behavior. I went to academia exactly because I agree industry has this problem. I remember that when I started in construction, the first time that I saw a wheelbarrow, I had an attack. I said, this damn thing has one wheel. This is stupid. Everything it's falling, and everyone looked at me and said, "We have a 45-floor building to build, and we are discussing wheelbarrow." And I would be designing the whole project. I was designing wheelbarrows, and this project was really behind schedule, and I was still designing my wheelbarrows. I didn't care about the project. I cared about the wheelbarrow, and this is when I realized I'm a researcher. I'm not an industry guy. And but when I go and work with my colleagues, I always remind them, you are someone that likes to think things that cannot be done. Don't do this. And then they feel embarrassed. They tend to change. Say, okay, you are right. And it's just attitude again.
Yes, this is a small group. We are a small group. For me, it's everything linked to the experience. Academic, executive, linked.
And I know we're running short on time, but I think at the root of the what you're describing is something I've seen in students. I've seen it in my colleagues. I've seen it in society, actually, now that I think about it. It's a societal thing. Probably in your society as well, too. There is a fear of failure. There is a deep-seated fear of failure. To fail is the worst thing. Everybody has to get an A. Everybody has to, if you fail at anything, that's like the scarlet letter that you have to wear around your neck. And I think that fear of failure makes us not take as many risks and take as many chances. It happens in the business world as well, too. In the 1940s and 1950s, you know how long it took us to turn out a new airplane? It took us maybe from concept to flying, maybe 2-3 years. 2 to 3 years. Right? You know how long it takes for a new aircraft to come out now? Decades. Decades. For America's newest non-commercial military fighter jet, the F-35, it took 25 years. 25 years. From 2 to 3 years to 25 years. Why? There's some acquisition problems and sort of logistics type stuff. But, you can't fail. Failure kill the program. We've lost that spirit of it's okay to fail, stub your toe, pick yourself up and keep going. I mean, so many people have said Moscow is going to fail, right? His production facility. They tried to automate the whole thing and they ran into production problems. They weren't hitting the targets. Everybody says he's going to run out of cash. Fine. I'll retool. I'll build them in the freaking parking lot if I have to, right? But I'm going to keep going. He recovers from failure all the time. And many leaders, too, the innovative, visionary type people that recover from failure all the time. I think we're too gun-shy about failing.
just want to add something. But again, one thing that makes the U.S. so different, okay, is that we are afraid of failing, but you are not afraid of failing in research. The U.S. it's very open for research failure, and it's understood in the U.S. that you are going to have 10,000 of PhDs that are going to end up in drawers, but you are going to have one Google, one thing that would come, and this is accepted there. And there is no embarrassment if I have an hypothesis, an idea, I do research, in the end, obviously that I follow the research methodology, I do the validation, everything, negating the hypothesis. It's not embarrassment in the United States. This is a problem in Brazil, okay? And I have Brazilian friends. If you go to CNPq and you get a grant, you get the safest possible one, because if you're going to write a report at the end of the research said it didn't work, you are afraid that you're never going to get another grant in your life. So this is a mentality that needs to change in the United States if you want to succeed. It has to change in Brazil if you really want to do impactful research, because research is a very risky business.
Sure. So I want to answer your question with two examples from Purdue. We never think inside the box. We take out of the box what we can, but it is it's taken for granted that you begin outside the box. You may end up jumping back into the box if that's the right thing to do. But we have to challenge ourselves and our students. And one nice model at Purdue was to provide students multidisciplinary from different engineering schools and science schools and social science schools and education schools team together and solve projects, problems for society. Those are societal challenges. They are grand. They are grander than what we are talking about here, because they are about individuals suffering, about parts of the city that are suffering, part of the states that are suffering, and other countries that are suffering. For instance, problems in Africa about bringing food to mothers that are supposed to be nursing and cannot get grain for their food. How do you solve those problems? Those are societal problems. They are great challenges. We're very happy to know that our students are extremely excited about them, and they are looking out of the box for solutions that benefit specific people and real problems. Not to mention healthcare and other problems, that those students develop devices, and even some startups came out of those projects. Now other universities are doing the same. So I'm just saying that at Purdue it was begun, pioneered, and proven very successful. It gives excitement, which is answering the issue of do we need to create another Tesla B, Tesla 3? Those are coming. And they have solutions for the top of society, which is necessary, because then you percolate down and everybody benefits. You have NASA grand challenges. Those invent materials, new mechanisms, new interfaces, new software that benefit society worldwide. So those challenges exist. We don't have to be so pessimistic. We just have to keep looking for more opportunities of doing that. So I think I gave you some examples of that, and of course there are many other good examples of from other universities that I've seen.
Okay, well, we are running out of time right now, so I would ask you, each one of you, to give a short final statement, and we finish the section. Professor Reddy, please.
You know, for the last 2 days, we've been talking about engineering grand challenges. And a lot of things that we said came from our own personal, professional research. But then I think I'm one of the oldest on the stage here. So I tend to be a little bit philosophical. So think about humanity. What is the role of engineering in humanity? Is to serve, right? So we have to serve the humanity. So what do we mean by that? So I think the food, shelter, healthcare, and then maybe defense. So those are the areas that engineers have to identify the challenges in those areas. So for example, when we talk about food, Now water will be part of that, right? So there are a vast majority of the people on the face of the earth don't have water, the drinking water, non-contaminated. So what are we doing? So membrane technology is one of the important things, right? And then, of course, how you collect the water, the natural water. See, that has to be also related to that. And then go on to shelter. And for example, civil infrastructure. So that means you have to come up with materials that are very easy and cheap. That means depends on the particular country or region. You don't copy America for materials because those would be expensive, right? So there has to be elements of this nature that has to be thought of challenges. So in creating a cementing material from the ash or whatever local products, and so 3D printing has to be taken into the same context. How do you create? See, for example, India and China. I think most of you know they piss off on the road. As they walk, they piss off. So they are trying to create these toilets. So making them cheap and accessible to people is one of them. See, one other part is the culture. Culture is something difficult for the engineers to change. And this is where collaborations come with psychology, sociology and all. Because even if you put a dustbin, there are a lot of people who don't walk to the dustbin and put it there. That is cultural issue. So going back to the elements, 4 areas I identified, like food, shelter, health care, and defense. Defense could be from natural disasters to invasions. That's a broader sense. So then you subdivide them into research areas, and I think many of the things that all of us said will fit into one of those categories. So that's what I want to say.
Okay, thank
you. So the grand challenges have to come from how we contribute to the societal needs.
Thank you, Professor Nath.
First, thank you. First, I would like to talk to the audience on internet or video streaming that we did not get any questions from you, but we all are welcoming you to look us up on the internet and email us the question so we can answer you in the future. We already have this collaborative intelligence available. I decided to devote for this summary panel the following word: share. We all agreed that sharing will be important to get out of the box, sharing previous knowledge with future knowledge and predicting solutions for the grand challenges. And share stands for the first item is share, SH, and the second one is augment, A, and the third one is rationalize, begins with R, and the last one is educate, beginning with E, so we have the share summary. So share means we are into the sharing economy, whether we like it or not. We cannot do it alone. We have to find ways to share resources, to share tools inside the factory, outside the factory, between factories, and we have to even share knowledge so that we can provide better solutions. The A, augment, also is about awareness. We augment what we don't have by adding awareness, using sensors, using knowledge bases, so that we understand our spatial location. We're all using navigation devices, so we need to also know our operational awareness. What are we operating on? What are we operating against? And so on. The rationalize R is for microeconomics, macroeconomics, social considerations, psychological considerations, in order to rationalize. During a transition from where we are towards solving the grand challenges, we need to rationalize what we're doing because we have limited time, limited resources. So we have to rationalize and not jump into playing with games unless we can rationalize and justify using them because the games are useful for us. The last one is educate. And here, the letter E from share, we're talking about education, but also we are talking about training, and we are looking here at sharing skills. Inside the factory, we are spending a lot of time training people to perform things that may be useful only for the day or a week. And we need to find ways to share that knowledge. Maybe they have that knowledge in another factory. Maybe we own the other factory too. Maybe we don't. Maybe a competitor owns it. We have to find ways to get sharing skills as part of educating, training on demand, not only starting ahead of time and training everybody for things we don't know will ever be needed. So to summarize, we have this share for the panel. My gift to you. Thank you.
And Aline?
First and foremost, I'd like to thank the organizers for inviting us down here. Been very educational for me, and I really think that this is a good step forward. There's really very little that I can say that hasn't been said already, or won't be said in the future in the journal, except for one thing that I would like to add. I think we've spent a lot of time talking about solving some of these grand challenges, whatever they are. As I said, you can sort of utilize that however you want to make your own project a grand challenge, and that's something that we have to be careful of. But and a lot of the solutions, I mean, there's the problem identification. The solutions that we've come up with have tended to be creating something. We must create something new, right? We must create. We must build. I have a rule in my house, and I think it's very, very appropriate here. As we go forward and we create all of this new stuff, we better make sure we clean up after ourselves, right? Yeah, a rule in my house is you make it dirty, you're going to clean it. You clean up after yourselves. As we move forward and supposedly solve many of these grand challenges, beware the law of unintended consequences, that you don't create something that then takes a whole lot more effort to clean up afterwards. I mean, this gets to a challenge of sustainability and environment, and that you could probably put it under that grand challenge. But I would caution, I mean, not caution, I would encourage, because remember, we're trying to encourage new visionaries and leaders, and we're cheerleading them to go out and address the challenges of the world. As you do that, please make sure you clean up after yourself. Okay. Now, that, like any of the other grand challenges, is going to be hard. If it wasn't hard, we wouldn't be sitting up here. What I will say is I really do appreciate the Politécnica, Springer, and the editor trying to put together a journal like this that is trying to look at these hard problems, because there are not that many places that are. And so I really do wish you the best of luck. I want to see you succeed. As a society, I think we need to see you succeed.
Thank you.
Very short. Thank everyone. Thank you guys for inviting us. Thank you all the panelists. That was really fun. Learned a lot here. I think that in the end we have to start understanding complexity, and that's the key for us to deal with the problems that you are trying to deal. Andrew just talked about the example of designing a plane that would take 2 years and taking 20 now. And if you ask them why, they said that the planes got much more complex. Same thing, the Empire State Building was built. They bought the land. They built in 1929, the tallest building in the world, in 18 months, from design, demolition of the existing Waldorf Astoria, and the construction of the building. We cannot replicate this today. There is no way that we can build a building that size in 18 months today. And people are going to complain about permitting in cities. They're going to say that, there was no central conditioning at the World Trade Center. There was not, the complexity was not there. It was just the simple concrete windows and done. They have 120 kilometers of elevator shafts in the building. And again, when you ask why can I do that, because buildings got much more complex. So I think that that complexity it's making us less efficient to do the simple things that we were doing before. So you are not even being able to do the things that we did before. But in the end, I just think that we have to make engineering fun. You have to bring fun back. There has to be really a fun business that we love to do it, and we are proud to do it, like in SpaceX. And I was at SpaceX the day that they landed back the barge, the thing, and I was really impressed. I think that I told someone here that I was there. The control room, it's a glass room, and there was maximum of 10 people working there, and everything was being done by 10 guys, and you are around 300, 400 people in the bar that it's behind, drinking beer and kicking a big ball and dancing and having fun, and again, was fun. You could see that they are working 10 hours because they are really having fun. They are laughing there, and they are all kids. And I looked around, I never felt so old in my life that those are all 20-year-old kids that they are doing because it's fun. We have to bring fun back, and to say things that I said yesterday and today, you have to keep creating the world that never was.
Okay. Last but not least.
Okay. As last, I'll thank you. The speakers we brought here special people with special abilities, and I'll end saying something. But one thing that I wanted to say is that somebody brought this idea of 50-year cycles, right? Professor Goldenberg and Andrew probably brought it again. This idea of it's a human construction, but it's an interesting number because we are talking about the cycle of energy is like 50 years. But when we think about 50 years, I was coming here, and that was very funny because I said, "Well, okay, now it's 50 years that we had the man and the moon, right? It's about that." And I remembered, and then you brought this idea back. That's something that brought people together, that motivated people. And I remember that's the famous speech by Kennedy. That's we chose it not because it's easy, but we chose it because it's difficult. So we lost something, or missing something over the last few years because we cannot put together people with the same drive. And that's important for the next generation. And when we say next generation, it's our mission. We cannot say next generation will do it. We need to teach the next generation to do it. Okay? And one thing that, so that means that time is now, is not thinking about what they are going to do. We need to teach them how to do it. But I will finish my talk because we discussed so much about great challenges. And then I reminded me one sentence that my supervisor, Professor Seipi, told me once. I went to his office and he said, it was a very famous apparel advertisement. He said, just do it. You remember this famous? So I put another challenge to you. We have so selective people here. Maybe we can do more than just a journal. Maybe we can try to put together a proposal that we have different people from different backgrounds. Maybe that's a challenge to us. Okay, instead of 14 challenges, maybe one challenge for us. Can we put together a subject that all of us can contribute? That's another challenge, maybe the 50th one. Okay, I'll leave at that point. Thank you.
Thank you. Well, in the name of the editorial board of Politécnica, I thank you all for coming, for accepting our invitation, and collaborating so much with making this new journal a reality. I think you saw the enthusiasm of Springer on that. So in the name of Springer, the editorial board, the Polytechnic School, and also the provost of University of São Paulo, I thank you all for contributing to make Polytechnic a new proposal, not only for us, but for the whole world. So thank you. I think we finished the session.
Gentlemen, thank you very much.
All right.
Pleasure.
Nice to meet you.
Thank you. Pleasure. A pleasure. And thank you for your help.
You're very welcome.
You've been very patient with us.